All right. Let us learn. We got to finish this one, which is part C and D of this question, and then we'll start polar coordinates functions, which I think you've seen before, but they're always like they're hard. They're like they take a good amount of thinking just to like remember how they even work. So you'll see. I remind you what they even are to start with, and then we'll do calculus on them. Hey Sawyer. But okay, refamiliarize yourself with this the question, example 5. It says a particle is moving and the position isn't given, but the velocity kind of is, the derivative of the position is. So you know that this is the velocity, what I underlined in blue. And then it says that at time 4, the particle is at the 0.15. We did A, we did B, and now C is asking find the y coordinate of the particle's position at time 6. So if they had asked us at time 4, then we would know the y coordinate, but of course that would be a strange question. So they asked us at time 6, but maybe you have an intuition that time 4 will give us some like insight into where the particle is at time 6. So before I give you hints, do you guys have ideas on how to find the y coordinate at 6? Let me write some stuff that I need up here. You guys have this page blank too, I think, so you don't have to squeeze it all into one page. Okay. At time 4, the particle's at that point. Then it's asking for the y coordinate at time 6. Any ideas? Or should I say? Okay, what if I'm not gonna say, but I will say this. Do you agree that them asking me for the y coordinate at time 6 is just asking me for y of 6? Agreed? Okay. Need y of 6. Do you also agree that we have y of 4? Okay. You don't have to write all this, but just so we're all on the same page. Y of 4 is 5. Do you also agree that we have not y, the y function, but we do have y prime, y dt? Okay. Let me write that down. Natural log 2 plus. Okay, now do you have ideas? Yeah, when you write it like this, it's like a lot of times, like I keep saying, a lot of times the wording of it is what confuses you guys. But if you break it down into this question, you've seen this 1,000 times this school year. Not 1,000, but without exaggeration, you've probably seen it 15 times this school year. Like throughout homeworks and tests and quizzes and reviews and stuff, you've seen this like for real 15 to 20 times this school year. So hopefully by now you caught on that how am I going to set this up to answer part C? Yeah, thanks, guy. I'm good. Okay. Okay. Yeah, right idea. Guy saying take this antiderivative, plug in. Oh, wait, hang on, you're missing a step. Because what I thought you were saying is take the antiderivative of this, you'll get blah 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 plus c. Use like y of 4 equals 5 to get the c value, and then plug in 6. That's what you're missing. But the flaw in that is that nobody knows the antiderivative of that. Like I don't think that no function can have this derivative. Like that we can't do that by hand, is what I'm saying. So other ideas? The fact that we got y of 4, we need y of 6. Oh, you guys. Okay, let this, your 21st time seeing this year, let that be the time where you finally get it in, like solidify it in your brain. That's when you're given a point and you're given the rate of change and you're asked for another point, the way to do it is you say y of 6 equals y of 4 plus 4 to 6 of y prime. Should I let me just so you feel bad enough to really learn it this time, let me go back to all the way back to 2 days ago and show you 3 different times where we did that exact problem. Starts with 800. Here's the rate of change. What's the 20th minute? Starts at 5. Here's the rate of change. What's the 3rd minute? Starts at pi over 2. Here's the rate of change. What is it at 3? It's the same thing that you saw 2 days ago, 3 times in a row. And then before then, and before then on your Unit 8 test, and before then in Unit 6. So it's like, I'm not lying when I say this shows up all the time. Here's another time where it shows up. Try to remember that, you guys. Very important. It's called, I keep calling it start plus accumulation. It's like, here's this point where I started, plus all the change that happened between 4 and 6. I don't know what the disconnect is between you guys seeing it a bunch of times and then getting asked again, and then you guys forgetting. I don't know. But let me know if I can like explain this better in some way. But anyway, this is what you're supposed to do. And then this is why I was saying this is helpful, because even though we can't take this integral by hand, this is a calculator question, and your calculator can say definite integrals, but not indefinite integrals. So that's why this helps to set it up like a definite. Okay, so then this would end up looking like this is what you type in for Desmos or your calculator. And you would get, if you type that in, you'd get 11.5705. Cool. All right, there's the y coordinate at 6. Then part D as in dog. Says, just so I don't have to scroll up, let me read it off my paper. It says, find the total distance the particle travels along the curve from 4 to 6. Again, this is another one that you just took a test on in Unit 8 for singular, like one-dimension motion, but this is no different. So for one-dimension motion, do you guys remember the setup for this? You remember? That is displacement, but this one is distance. Yeah, so nice. Yeah. The absolute value of this. And where does it say 4 to 6? Yeah. Integral from 4 to 6 of that. Cool. Okay, same thing here, except that you have to remember that now we're talking about vectors. So the absolute value of a vector is, do you guys remember? Nice, yeah. Yeah, so you have to get the magnitude of the velocity vector. It's annoying that it's on a separate page, but let me remind you that the velocity vector was derivative, comma, derivative. So they gave it to us in a different form. But just to help me teach it, let me write it in this form. That was our velocity vector. That was dx dt, comma, dy dt. Again, they gave it to us in 2 separate equations, but hopefully you were able to like extrapolate for yourself that this is the velocity vector, meaning that the magnitude of it would be, remember, square root of the x part squared plus the y part squared. So literally this function squared plus that function squared. And if the last one was ugly to do by hand, this one is way, way, way uglier, like not possible. So you would type that into Desmos, and Desmos would tell you that the total distance would be 12.1362. Okay. And if I didn't want to get to polar coordinates, I would pull up a bunch of years in a row, 2021, 2022, 2023, 2024 of the AP test. And I would show you that each of those, in fact, if we have time at the end, I'll actually do it. But each of those years, like for 4 or 5 years in a row, ask this question in like very, very, very similar form, just maybe different functions. But usually it was like a particle's moving, here's the derivatives, in other words, the velocities. And then parts A, B, C, and D were like all almost the same. Like find the position, find the acceleration, find this, find that. Usually pretty similar. So if that comes back this year, remember I said that they took it away last year. But if it comes back this year, then as long as you know this stuff, then you're good on that question. That's 93 points, hopefully. Cool. Okay, vector functions done. Questions on those? Okay. All right. Vector functions, in my brain, I'm like, well, I don't know if I fully understand vectors, but like I said, you can just think of them as parametric equations. They're no different. There's just a comma in between them. And use what you already know from unit 6, then 8, and whatever to answer these questions. And it shouldn't be a super huge deal, like a super heavy load on your brain to memorize all these things. All right. And then another thing that is always like makes people uncomfortable is talking about polar coordinates, but that's what we got to do today. So polar coordinates, for sure, before AP pre-calculus, like before we started doing AP pre-calculus, you guys were like, students were doing that in pre-calculus. But did you see polar coordinates in last year in AP? Okay, all right, good. Okay, so at least you're familiar with these. In case you forgot, polar coordinates are like, instead of traditional coordinates, where you're basically telling me take 3 steps this way and 2 steps up, and now you're at the point 3, 2 on the XY plane. Now you're telling me start looking due east, now rotate 25 degrees and walk 7 miles. And that's how polar coordinates work. Rotate and walk this much. That's polar coordinates. It's in a nutshell. This kind of just explains what polar coordinates are, but you've seen them before, so hopefully my summary was enough to bring back everything you needed. And then in the image shown, the coordinate is the point 4, pi over 4, again, because you rotate pi over 4 and you walk 4 radii, or like 4 circles away from the origin, and you end up at this point. But again, to remind you how these work, because it's probably been a while, we are first just graphing like polar coordinates, just to like remind you how these work. So 3, pi over 6, obviously this is radius, angle. So I guess you could do these kind of in either order, but I don't know. For me, I like rotating to the angle first and then walking the 3 radii rather than walking the 3 radii and then rotating the angle. So let me do just that. Notice that this is, look at, here's the coordinate plane, like X and Y. So that would mean that this is pi over 6, this is 2 pi over 6, and it's missing pi over 4 for whatever reason. So let me put pi over 4 right there. You're never asked for it, but just so we're all on the same page, like this is pi over 6, 2 pi over 6, 2 pi over 3, pi over 2, etc. So pi, don't count his second printed line as pi over 4 is all I'm saying. All right, anyway, 3, pi over 6 would be rotate to the line of pi over 6. There it is, and then go 3 radii towards it. 1, 2, 3. Here's the point A. Okay, Then B, same thing, rotate to pi, boop, 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 boop. There's pi, and then 4 radii towards it, 1, 2, 3, 4. There's point B. Point C is only funky because of the negative angle, but remember what that means is instead of rotating this way, you rotate in the opposite direction. So negative 5 pi over 6 would be 1, 2, 3, 4, 5 pi over 6, and then radius 3 on that line. 1, 2, 3, boom. That's point C. I don't even see you guys writing, so you guys must be ahead of me, but in case you needed the reminder. And then orange point D, remember negative radii mean go away from, or maybe you were taught it differently, but the way I think of it is go to 3 pi over 2, which is right here, and then go 2 away from that line. So not boom, boom, but boom, boom, upward right here. That's D as in dog. But it looks like you guys remembered that anyway. Yeah, nice. You guys, good job. Okay, so that's polar coordinates, the reminder. Then more reminders. Again, this is not something that you'll get asked on the AP test, but it gives you an idea of how polar coordinates work. It gives you like a better understanding of them. So it wants us to change the point 2 comma pi, which would be, oh wait, but I want to change this. Listen, don't, if you worked ahead, change this to pi over 6. Just because then you can see the actual right triangle and why everything is the way it is. So change that to pi over 6. The point would be this right here. And then do you guys remember anything about converting this to the point x comma y rather than r comma theta? Okay, good. Okay, good. I didn't want you to be bored as I went through this packet. So James, you remember?
Yeah, the angle and
Yeah. Yeah. Okay. So first of all, just so you guys understand, like James is talking about a hypotenuse because what we want is this x coordinate, which is just this length, and then this y coordinate, which is just this length. So he's talking about, oh, this makes a right triangle, and I already have the hypotenuse is 2, and I already have that this is pi over 6. So therefore, yeah, you can do some trigonometry and get the x and the y coordinate. I'll let you guys maybe think about why this is the case or how this works. But you can believe me when I say I don't think it'll take much convincing, but the x coordinate is always going to be the radius times the cosine value. Again, if you think of the unit circle and just scaling it by whatever radius you're at, that should make sense. R times cosine of theta. Again, on the unit circle, cosine is x. Scale it by whatever the radius is, and then we get this new x value. And then y would be r times sine of theta. And these are just big, good, important things to know for what you will be asked on the AP test anyway. That's just good to know, but also it helps us convert into polar coordinates. So now if I want x, I would say that's equal to up 2 times cosine of pi over 6, which will be whatever it will be, and then y would be 2 times sine of pi over 6. Okay, so 2 times cosine of pi over 6 is the longer one. So radical 3 over 2, nice. So this would be 2 times square root of 3 over 2. Boom, there's my x coordinate. And then this one would be 2 times 1/2 for the sine of pi over 6, which would be 1. So altogether, it would be the point square root of 3 comma 1. Nice. And then here you can see that this is why I was talking about changing this from pi to pi over 6, because then you can actually see this right triangle. And then it's very obvious that you can do trigonometry. But like I said, this works for any angle, not just if you can make a right triangle. Even if you were at pi and you can't make an obvious right triangle, this like converting will work. Cool. All right. So that's translating points from polar to rectangular. But you can also, a lot of times, not always, but you can always, or sorry, you can often express polar functions as rectangular functions. And for that, you need to remember the same two things. So that x is equal to r cosine of theta, that y is equal to r sine of theta. And putting those two together and using the Pythagorean identity that sine squared plus cosine squared is equal to 1. This guy is also true. I'll let you play with that later and verify that it is true, or like think about why that's true. But these are the three things that if you know those three, you can usually convert your equations. So look at, it says, what is this function going to be in terms of x and y? So knowing that you would like to get one of these guys in there, one of these three big identities, do you see a way to convert this? It may be that you guys have to introduce some stuff, like you might have to force one of these to be in there. But if you don't see what I'm saying, I'll give you my hint. Yeah, it looks like you guys don't see it. But the trick is usually, like I said, force one of these to be in there. If I see a cosine of 3 times cosine of theta there, oh well, if that just had a little r in front of it, then I know that this is x. So if I just multiply myself by r on both sides, okay, that's me multiplying by r on both sides. Then on the left, I get r squared equals 3r cosine of theta. And I have identities for both of these. R squared is this dude. And r times cosine of theta is that dude in yellow. So I can change both of these to x squared plus y squared equals 3 times x. And now I've done it. Now it's in terms of x, y. Yeah, in fact, let's just leave it there. Okay. You can mess with that and see what type of, well, actually, without messing with it, if you just look at that equation, do you know what shape that, or like what the graph that would be, what the blue function we just made? Nice. Yeah, nice. Hazel's saying it's a circle, or maybe it's an oval, but I think it's a circle. In fact, I know it's a circle, and if you wanted to verify, then watch this. You could do, first, let me do the polar one, r equals 3 cosine of theta. Oh, and this is good learning for you guys too, is that if you want a polar graph on Desmos, you can type in the word theta, theta, and it comes up with that. And we get this circle. And if we write our equation that we got after that, like by translating it, we get the same circle. So we did a good job. Nice, y'all. Good job. Okay. And then this one, they want us to convert as well. Now that you know kind of the trick is to force one of these to be in there, do you see what you can do? You guys are working. What are you doing if you're working at that? What are you doing to this function? Please, what do you do?
I did that like CSC theta A the same as 1 over sine of theta.
Remember that? Let me get there. R equals 2 over sine of theta. Remember, cosecant is 1 over sine. It's the same, like, that's how it's defined. And so therefore, what do you do after that?
And then I divided by r on both sides.
Oh. Okay, yeah, sure. And now you have this r sine of theta right there. This guy, this is what I was trying to do. That guy is equal to y up there. So you get that 1 is equal to 2 over y. Which works fine, but more like another way to write that would be y equals 2. I thought what you were gonna say, Charlie, is multiply by sine here. Get this over there. You get r sine of theta equals 2, which would be y equals 2. But your way also works. All right, y equals 2 should be a horizontal line. Here's us checking r equals 2 cosecant of theta. Nice, horizontal line. Y equals 2 is also a horizontal line. 1 equals 2 over y is also a horizontal line. Do any of those work? Cool. And now many minutes. How many is that? 10 minutes to graph a function ourselves. Yes, let's do it. It's easy. So watch this. In case you forgot how these, what's up? Yeah. In case you forgot how these go, like there's, look at the next page tells you some like shortcuts to take. If the graph looks something like this, then it'll be a circle. If the graph looks something like this, then it'll be a circle, or it'll be whatever. Here's cardioid, here's whatever. But there's so many little rules, even like something that looks the same way. 1 plus 2 sine of theta will look something different than 2 plus 1 sine of theta. So to me, that's just way too much to memorize. I don't have these in my brain ready to go. What I have to do every time is just like trace along and graph it. So the sure way to do these every time is to make a little table, which is what I want to do. Okay. And here the independent variable is theta, so that's the one I'm choosing. And depending on how confident you are on these, you may need to do like every single like 0, pi over 6, pi over 4, pi over 3, pi over 2, like do every single one so you get a good picture. But if you're a little bit confident with them, then you could skip some of the in-between ones and just do 0. Let me go somewhere in between. Let me do 0, pi over 4. Let me do all the pi over 4. Pi over 2, 3 pi over 4, 4 pi over 4 would be pi. I don't know why this is pi over 2. Should be pi. 5 pi over 4, 6 pi over 4, which is 3 pi over 2, and 7 and 8, which is 2 pi. Okay. And then you get the value of each of them. You put the points where they go, like just like we did at the beginning of the packet, or like at the beginning of this section. And then connect them with a good idea of whether you're growing or shrinking and where is it 0 and where is it negative and all that stuff. And then you get a good graph. So here's us doing that. This one's not that hard. So plug in 0 and I get 1 plus sine of 0 is 1. Sine of 0 is 0, 1 plus 0 is 1. I don't know how much unit circle you remember. But that's all I'm doing is I'm plugging these in. So pi over 4 into that would give me 1 plus square root of 2. Which is how much? Let me check. Square root of 2 is that much plus 1 is 2.4. No, that can't be right. Oh, I'm stupid. I'm sorry. I said square root of 2. I said square root of 2 over 2. Sorry. This would be like 1.7. Something. And then pi over 2 would be 1 plus 1 is 2. 3 pi over 4 would be 1 plus square root of 2 over 2 again. Okay, I have to do it weird on this. It's 2 square root of that. Divided by 2 is that much. Plus 1 is the 1.7 that I was getting before, if you didn't believe me. Pi would be 1 plus 0, which is 1. Pi over 4 is finally negative, so that would be 1 minus the square root of 2. Over 2. Dang it. Okay, 2 square root of that equals, divide by 2 equals 1 minus this. Let me just subtract 1 and get positive 0.3 about. I did it weird on my calculator. 3 pi over 2 would be 1 minus 1, which is 0. 7 pi over 4 would be, again, this 0.3. And 2 pi would be 1 plus 0 is 1. Okay, you good with the plugging in? Okay, and then now again, you're just plotting a bunch of points like you did earlier in the packet. So theta 0, r is 1, is right there. Theta pi over 4, 1.7 would be just before 2. Then 2 at pi over 2. Am I too fast? Then 1.7 at 3 pi over 4. Then pi comma 1, so pi comma 1. Then 5 pi over 4 is 0.3, so not even to the first circle there. Then 3 pi over 2 is 0, so right on the origin. So that's called the pole on polar. Then 0.3 again, and then back to 1. So the thing would look like connecting all these, it would look like this. Which kind of looks like a heart, which is why they call this a cardioid. Okay. A question I would have before I let you go. A question I would have if I had just done this with my teacher and he drew this on the board is I would say, how do you know that this was the top of the thing? Like, how do you know it didn't go like this red one, which I'll undo in a second. Don't draw this red one because it's wrong. But I would be like, how do you know that it didn't look something like this? And then it came back or whatever. How do I know that? And if you have that question, or if you now have it because I introduced it, then let me tell you, you can always check yourself by plugging in more numbers in here. So pi over 6 and 2 pi over 6 and all that stuff. You could always do that if you wanted to, just to make sure. But the other way I can tell you is this. Like, this might be extra work, but it might help you do it, or it might be an alternate way to even do it. Like, you might not even need the table if you like this better. So another way I've seen people do this is they graph this as if it was y equals 1 plus sine of x, like a normal rectangular function. And then that kind of tells you, oh, okay, this gets big and then it gets small, and the biggest it gets is 2, etc. So if I graph that real fast without going into the details, remember what that would look like is the midline would be 1, it would go up to 2, and then down to 0. So it would look something like this. Back and forth and back and forth. I guess this would be a pi over 2. This would be a 3 pi over 2. It's at 1 at 0 and at pi. And then back to 1 at 2 pi. So if you graph the rectangular version, then you can see, okay, at 0, I should be at 1. Then I grow till I get to 2. So get bigger.
Yeah.
Get bigger till I get to 1 at pi over 2. Then get smaller till I go to 0 at 3 pi over 2. So what we did is actually, so some people like graphing the rectangular and translating that to polar. Some people like the table. Some people like putting a bunch of values in. I don't know what you guys like, but all of those are options. All right, cool. Tomorrow or Monday we'll do number 2, and then we'll start doing calculus on these. Again, you won't get asked to graph these, but you will get asked to do calculus on the graphs of these. So it gives you a good intuition on how to do that calculus if you know how to graph them and verify what the graphs look like, etc. All right, good work, y'all. Monday we'll continue this.